Okay, in this clip what we're going to look at is the topic 5, which is all to do with fuel. So this is one of the most important areas of chemistry because obviously this relates to the whole idea of energy and to global warming. So first of all, what we need to start off with is the definition of what a fuel is. So a fuel is a substance that can be burned to release heat or energy. Okay? So that takes us back to this idea about how do you actually get something to burn. And you may remember from first and second year that there is a fire triangle. Okay? So you need a fuel, which is what we're just talking about. You need heat and you need oxygen. So all those three things are needed together to get fire. Okay? So not only do you need the fuel, but you need to heat it up and you need to have oxygen there for it to burn. So if we come on to the fact that where the oxygen actually comes from, and obviously that's going to come from the air, so you have to remember a little bit about the composition of the air, and it is roughly 78% nitrogen and only about 19% oxygen. Okay, so only about a fifth of the air is actually oxygen, which is what we need to get things to burn. Okay, and that's going to be important for the bits that we come on to. So that leads us on to what kind of fuels do we actually have? Well, you might be familiar from other subjects that one of the common fuels we've got are something called fossil fuels. And obviously that's a fuel derived from fossils. So essentially what we're talking about there is coal, oil and natural gas. And these represent a huge amount of the energy that we need in the world, okay? These three things, these three fossil fuels. So first of all, we've got to try and understand where do they actually come from, why they call fossil fuels, and what the process is for their formation. If you look on your absorbed chemistry program that you've got in your CD, you can go into the contents just to show you that, and you can go down to, scroll down on it. You can go into Introduction to Crude Oil, which is what was in there, and there's a little animation there showing the formation of oil. Okay, so you can read through that and see what happens. So if I press the green button, you can see the stages of crude oil formation. If you go back and look at it, it's more of a kind of how you'd answer it in an exam question. Well, there's kind of four kind of half parts to it, so 4 half marks for the formation of it. And the way I like to remember about it is that it's kind of like the princess and the pea story. And if you're not worried about the princess in the top, and if you think about the poor wee pea at the bottom, it's got 100 blankets on top of it, which represent the layers of rock. Now, if you're that poor little pea, you'll be under an immense amount of pressure because you've got all these 100 blankets plus the princess sitting on top of you. It'll be incredibly hot because of all the layers of blankets, and there won't be much air because you're getting trapped underneath all there. And that's the ideal conditions for formation of oil and coal. The only difference is it's not a pea. In the case of coal, it's a plant, and in the case of oil, it's tiny sea creatures. So essentially, if you're looking at the formation of oil, then the first thing is that we've got dead sea animals. Okay, and they sink to the bottom of the sea. Okay. Over time, layers of rock build up on top of them in mud. Okay, so layers of mud and rock build up over millions of years. Okay, so this process does take an awful long time. And then because you've got all those layers of mud and rock and you've got over that length of time, then what you've got is heat and pressure, okay, that cause the oil to change, or the cyanures to change, and the lack of oxygen. So the key things are then that there's heat, pressure, lack of oxygen, all caused by the layers of rock building up. It takes millions of years to take place, and it's formed from dead sea creatures. Okay, and that's the formation of oil. If you want to do coal, then all you've got to do for coal is the same process, apart from it's not sea animals, it's plants. Okay, and obviously that they won't sink to the bottom of the sea, they'll just get covered under layers of mud and rock on land. Okay, and natural gas is like a byproduct of this whole kind of decomposition process. So natural gas is usually found with coal and oil because it's a kind of byproduct of the whole process. So you always get coal with natural gas or oil with natural gas. And if you look at any sort of photographs or film clips of oil rigs, you sometimes see the flare coming off the top, and that's the excess natural gas being burnt off when they're extracting oil. So this process is continually happening. The only problem is that it takes millions of years. So the rate that we're digging up the coal and extracting the oil is a lot faster than it's been reformed. So that's how we get our fossil fuels. And what we want to look at is then, what are they actually made up from? So the only way, or the easiest way to try and find out what's in a fuel is to burn the thing and to collect the stuff that comes off of it. So you can do a little experiment in the lab where you get a funnel, okay, you put a fuel in there, let's say it was a lump of coal, okay, so it's a lump of coal. And so when you burn it, anything that comes off of the burning will go up through this funnel, okay, and it's going to catch it. And what we're going to do is take that through into a U-tube. And the U-tube is going to be surrounded by ice. Okay. And then the next thing we're going to do is we're going to take it into a boiling tube. And in the boiling tube is going to be lime water. Okay, now what we'd have attached to here is a pump to help suck through the gases as they go through. So what you find in this experiment is that when you burn coal or oil or natural gas which comes out of the Bunsen burners, the gases come through. What you find is that in this cold U-tube, because there's ice there, you see a liquid building up. Okay? And the lime water here turns cloudy. Okay? There's only one thing that turns lime water cloudy, and that's carbon dioxide. So we know that the coal must contain elements that can make carbon dioxide. Okay? And this liquid in here, obviously it turns into a liquid because it's obviously a gas that comes through here, but it's a gas that turns into a liquid, and we need ice to cool it down, so it can't be any lower than 0 degrees. Now what you can do is there is some chemical tests for water, one of them being anhydrous copper sulfate. Okay, it's white and it'll turn blue if there's water, so you can test that with copper sulfate. And what you find is that it is actually water that's in there. So what we make when you burn coal is you get water and carbon dioxide. But remember that to burn coal you need oxygen. So essentially coal, and you can do the same with oil or natural gas, you always get water and carbon dioxide. So if we think about what does that tell us must be in the coal or the oil or the natural gas? Well, carbon dioxide can only be formed if you have carbon and oxygen. Okay? Now the oxygen can obviously come from the air, but there isn't any carbon in the air, because if there was carbon in the air would look black, because carbon's black. So the only place that carbon could have come from to make carbon dioxide is from the coal or the oil or the natural gas. Water is obviously H2O, it's hydrogen and oxygen, and again the oxygen could have come from the air, but the hydrogen, there's no hydrogen in there, because anytime you ever light a match or a cigarette lighter or anything like that, it would explode, because hydrogen explodes when you light it in air. So the only place that the hydrogen to make the water could have come from is the coal. So what we know is that from this experiment that the fossil fuels contain hydrogen and carbon. Okay? We don't know they contain oxygen because the oxygen could have come from the air, but we've done other experiments and it confirmed that there is only hydrogen and carbon. Okay? So they contain hydrogen and carbon only. So the compounds we call hydrocarbons. Okay? Because they contain hydrogen and carbon only, so we call them hydrocarbons. Now, the other problem with burning fuels, so apart from getting carbon dioxide, which you probably know is a greenhouse gas, there can be other stuff that you get out from the fuels, depending if there's any impurities in the fuels themselves. And quite a lot of coal contains the element sulphur. So if you've got the element sulphur in the fuel, then obviously you're burning the sulphur as well, and that'll make sulphur dioxide. Okay? And sulphur dioxide, apart from being quite, it will choke you, set off your asthma if you've got that, it also dissolves in water to make an acid. Okay? And that's how you get acid rain. So if that sulphur dioxide gets released into the air, it'll go into the clouds, it'll dissolve in the water in the clouds, and it'll form acid, and that'll lead you to acid rain. Okay? And obviously the problems with acid rain will be that the acid can dissolve buildings, it can kill trees, plants, and also go into the likes of rivers and lochs, and it'll change the water there to become acidic, and that'll kill the fish. Okay? So the problems associated with that is it'll dissolve rocks, okay, like in buildings. And that happens, or it's happening in Athens, the Parthenon in Athens and stuff like that. They've tried to reduce the amount of car traffic in the centre of Athens to try and reduce how much that building is degrading because of the acid rain caused by the cars burning petrol, which comes from oil. Obviously it can go in and kill trees, plants. And it can all go into rivers and lochs, and that will kill the fish. It's a particular problem in Scandinavia because our pollution that we create gets often carried in the wind, and it gets actually carried over to the likes of Norway and Sweden, and the rain falls there, and our acid rain actually falls on those countries even though they're not responsible for it, and quite a lot of these problems are being present in the likes of Norway and Sweden. The other problem that we can get is that if we're trying to burn the things, particularly if it's a car engine, what you need to do is you need to get a spark for it to light. Okay, so in petrol engines, you might know that they've got spark plugs. Okay, and that spark plug essentially works giving out a little spark which will make the petrol and the oxygen in the air react. Okay, but that little spark can also cause, okay, so these spark plugs, okay, also cause the nitrogen in the air, which is very, very unreactive, and the oxygen in the air to react to make nitrogen dioxide. Okay, and again, nitrogen dioxide, just like sulphur dioxide, can go in and make acid rain. So if that reacts with water in the air and in the clouds, you get acid rain and you get the same problem. So cars cause this problem all the time, because every time the spark plugs are firing to burn the petrol, you're making nitrogen dioxide. So we've got some problems in with the hydrocarbons, the coal, oil and the gas. Okay, there's some of the problems with them. We can look at how we can solve that problem, and one of the ways that we can solve the problem is by using catalytic converters. Okay, and I think virtually all modern cars have these catalytic converters attached to their exhaust pipes. And what they are it's like a honeycomb structure, so what you've got is like a mesh like that. So you can imagine this is looking at straight on, and the exhaust gases would be coming flowing through this mesh. And on this mesh it's coated with things like platinum, palladium, rhodium. Okay? These are all transition metals. Okay? They're quite expensive ones as well, and that's why catalytic converters are expensive. And basically what happens is when you start your car, it starts to heat up this gauze, or this kind of mesh of these metals. And as all the pollution comes out, and think about it, what we've got is carbon dioxide, we've got carbon monoxide, which happens when you don't have enough oxygen, and we'll look at that one in a bit more detail. You've got your nitrogen dioxide, okay? You've got sulfur dioxide, and you can have some unburnt hydrocarbons as well. So there's a lot of pollution that could come out from a car exhaust. Okay. Now the carbon dioxide, this will have no effect on it. Okay, so the carbon dioxide will always get will always get released. So unfortunately, it won't do anything for that one. But what it can do, the carbon monoxide, it will convert that into carbon dioxide, which you think, well, that's still a problem. But carbon monoxide is poisonous to humans. All right, it suffocates them and they die. So carbon monoxide is converted into carbon dioxide because that's less harmful to humans. The nitrogen dioxide, well again, which caused the acid rain, basically what the catalyst can do is convert it back into nitrogen and oxygen. And that's okay because that's just the air again. The sulfur dioxide, it can't do anything with that one, and it can't do anything with the unburnt hydrocarbons. Well, obviously things like sulfur dioxide are only going to be formed if there's impurities in the fuel. So we can solve that problem by purifying the fuels. So if we purify the fuels before we put them into the cars, then we should eliminate that problem. If we make the cars more efficient by increasing the air to fuel ratio, okay, there's something called a lean burn engine. And basically what that means is that more of the hydrocarbons could be burnt. And that's better because you'll actually get the energy from them, which will make your car go further, and it saves all these hydrocarbons going straight into the air. Because again, they can cause global warming and the greenhouse effect as well. So that's the problems that we've got associated with them. But what we've got to remember is that these coal, oil and gas are vital for the whole economy of the world, and we'll just look at why they're so important just now. The hydrocarbons then that are present in the coal, oil and gas, well, the things like coal and oil are mixtures. Well, we should call this crude oil, okay, because it is our mixtures of about roughly 200 different hydrocarbons. Okay, and that's a huge mixture of stuff in there. Now, not all of it's useful. Some of it's useful for one thing, but not another, and vice versa. So, what we've got to do is look at how can these hydrocarbons be separated out. So, we've got to try and split up these 200 different hydrocarbons into smaller groups so that they can be used more efficiently. So, how do we do that? Well, one of the things that's different then, if we've got 200 different hydrocarbons, is the structure of them themselves. So what is useful to look at, and this is a wee bit to do with topic 6, which looks at the hydrocarbons in particular, but I think it's appropriate just to do at this stage, is to look at how do we separate the hydrocarbons. Okay. Well, the first way that we do that is by separating them into families. Okay. So there are three families of hydrocarbons. If you go into study intermediate 2 or higher, you'll find out that there's more families of hydrocarbons, but for standard grade level, we only have to look at 3. And they're given the names alkanes, alkenes, and cycloalkanes. Okay, so that's the names for the 3 families. Now, the posh word that we use in science or in chemistry for a family is a homologous series. Okay, now what a homologous series is a family, but what we mean by that is compounds with similar structures and reactions. Okay, so they're related to each other because they do the same kind of reactions. So what we want to do then is, how do we differentiate between the alkanes, the alkenes and the cycloalkanes? Because we know they're all hydrocarbons, which means they only contain hydrogen and carbon, so there must be something slightly different about them. So let's deal with the alkanes first of all then. Now, just because they're members of a family, just like in families that you're given your first name and you're given your surname, and your surname will be the same for all the members of your family. And the surname for the alkanes is Ain. Okay, that's their surname. So all the members of the alkanes will end with Ain, because that's their surname. But their first name will depend on what member of the family they actually are. Okay, so all hydrocarbons are given first name and surname. Okay, now the first name will depend on the number of carbons in the actual molecule. Okay, so this depends on the number of carbons. In the molecule. Okay, so you have to remember this list, although there is a little bit of a cheat which I'll show you that's in the data booklet. So, if the number of carbons is 1, then the first name is meth or meth. Okay. If there's 2, it's eth. If it's 3, it's prop. If it's 4, it's but. Okay. So they're a little bit different because there's not really an easy way to remember it. After that, it gets a little bit easier because 5 is pent, just like pentagon. 6 is hex, just like hexagon. 7, hept, and 8, oct. So these last 4 there are kind of like the shapes, so that makes them a little bit easier to remember. Now, these first names apply to all the hydrocarbon families, the alkanes, the alkenes, and the cycloalkanes, so that kind of cuts down the amount you have to remember. So, all we've got to do then is, if we've got an alkane, it's got 2 carbons in it, then its name will be ethane. Because remember, the surname is always the same. So, if we were to name all the first 8 alkanes, then all we've got to do is stick the word ane onto the end. Okay? Methane, ethane, propane, butane, pentane, hexane, heptane, octane. Now, as I was saying, there is a little cheat for that, and if you look in your data booklet, I think this is page 6, you'll see that order: methane, ethane, propane, butane, pentane, hexane, heptane, octane. So that's in order: 1 carbon, 2, 3, 4, 5, 6, 7, 8. So if you get rid of the ane bit at the end, then it doesn't matter what hydrocarbon family you're looking at, the alkenes or the cycloalkanes, you can see the first names there. Okay, and as I say, that applies to all these families. So that's the names of them. What do they actually look like? Well, if it's got one carbon, then carbon's in group 4, so it has 4 electrons around the outside. Okay? And hydrogen is in group 1, it's only got 1 electron. So the E2 and the A2 can match up and then form a covalent bond. Okay, but that carbon still has another 3 electrons it needs to fill up. So what you need to do is take an extra carbon, an extra hydrogen for each one of those. Okay, so the structure, instead of drawing it in this kind of elaborate way, which is kind of like what we did in some earlier topics, what you have to do there is that can be simplified to that. Okay, so that's the structure of, well, it's only got 1 carbon, so it's meth, and it's an alkane, methane. Okay, so that's the structure for methane. If we look at ethane, it's got 2 carbons, and what happens, the reason that we can get so many of these compounds is that carbon can form bonds to itself and make a chain. So there's ethane, propane, and remember that every carbon, because it's in group 4, must have 4 bonds. So if we go back and check it, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Okay? Because remember, group 4, 4 electrons. So it gave 1 electron to each one of those bonds. Okay? So that was ethane, propane, and just do the 4th one. Which would be butane. Okay, so that's butane. Now, what we've got then is the structure for them, okay, showing all the bonds. So that's called the extended structural formula. Okay. But sometimes, if we're writing equations and things like that, we don't want to draw out the whole structure, we just want its formula. So what we can get is what's called the molecular formula. Okay, so the molecular formula just tells you the number of carbons and hydrogens. This one's got 2 carbons, so it's C2, and it's got 6 hydrogens, so it's C2H6. This one is C3H1, 2, 3, 4, 5, 6, 7, 8. C3H8. And this one's got 4 carbons, 4, 8, 10 hydrogens. C4H10. Okay. But can you see how there's a little pattern? 2, 3, 4, 6, 8, 10. So you should be able to predict that the next one should be C5H12. Let's just check if that's the case. 1, 2, 3, 4, 5. Hydrogen, hydrogen. Okay, I've got it all in there. So 5 carbons, 5, 10, 11, 12. So it is C5H12. So that means then, although we only have to study the first 8 of the alkane family, we could predict the other members of them. Because what we can get is a general formula for the alkanes. And basically the general formula will allow us to work out the number of either carbons or hydrogens depending on what one you know. So for example, if we knew that there was 4 carbons, how could we work out the number of hydrogens? Well, the pattern you've got is, I've got to write this in, it's Cn, so whatever the number of carbons is, the number of hydrogens will be double that plus 2. 2n plus 2. Because if you look, 2 times 5 is 10, plus 2 is 12. 2 times 4 is 8, plus 2 is 10. 2 times 3, 6, plus 2 is 8. 2 times 2 is 4, plus 2 is 6. So that's the general formula of the alkanes. So if it is an alkane, it must fit that pattern. If it doesn't fit that pattern, then it's not an alkane. Okay, so you need to know that formula, CnH2n plus 2, where n is just a number. If we look at the alkenes then, there must be obviously something different with an alkene compared to the alkane. And what makes the alkenes different is that they have something called a functional group. Okay, and the functional group means a part of the molecule that is involved in reactions. Okay. So the functional group for an alkene. Alkenes are actually more reactive than alkanes, and it's strange because they've actually got a carbon-to-carbon double bond in them. Okay. And although that should keep the carbons together more, and it does actually make it more reactive as well. Okay, and we'll see some of their reactions later on. So, carbon-to-carbon double bond, what we want then is that must be present for it to be an alkene. So every alkene must have this bit in it somewhere. Okay, now going back to a rule that every carbon must have 4 bonds, well this carbon's got 2 already, so is that one. So we can only take 2 hydrogens here. Now, the other reason is, because you have to have a carbon-to-carbon double bond, you must have at least 2 carbons. So the first member of the alkenes, because it's got 2 carbons, is eth. So remember that's a prefix for 2. And its surname, well, is ene. This is ene. Okay, so that's its extended structural formula. Its molecular formula would be C2H4. Now we can have a look at the next member. So again, it has to have that part in it, but then you need to stick another carbon on, just like the alkanes. So again, let's add the hydrogens in. So this has got 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Okay, so that's the second member. It's got 3 carbons, so it's prop and E. Propene. Okay, and its formula is C3H6. Okay, I'll just do one more so you can see the pattern. 1, 2, 3, 4. So I'll stick the double bond in. It doesn't matter actually where you stick the double bond, although it will do. It will make a slight difference when we get towards the end of the topic. So 4 bonds in each carbon. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. And again, it's got 4 carbons, so it's but. And it's got the double bond in it, so it's ene, butene. And that's C4H8. So again, if we're going to talk about a general formula here, then it's relatively straightforward for this one because it's always double. 3 and 6, 4 and 8, 2 and 4. Okay, it's always double. So the general formula for these guys is CnH2n. Okay, so whatever the number of carbons, the number of hydrogens will be double it, and that's it. So it's pretty straightforward. Now, our last family then was the cycloalkanes. Cycloalkanes. Now, obviously they've got the word alkanes in them, so they are similar to the alkanes in some ways, but they've got this word cyclo. So the word cyclo indicates a ring. Okay, so basically what we've got to try and do is get an alkane and turn it into a ring. Now the smallest one you can do that with is if you've got 3 carbons. So you can turn them into like a triangle. Okay, a ring like that. And again, if we go back and put the number of hydrogens in, well, it's already got 2. Okay, so now every carbon's got 4 bonds. And again, if we write its formula, it'd be C3 H1, 2, 3, 4, 5, 6, H6. Okay. Now what would its name be? Well, this one's name, it's like propane, because remember we said it's like an alkane, so it's like propane, so we call it propane, but it's in a ring, so we've got to put the word cyclo. So this is called cyclopropane. Okay. And again, we'll do it with 4th member. 1, 2, 3, 4. Again, always trying to put them into this kind of ring. So 4 carbons, 2, 4, 6, 8. And again, it's based on butane, so it would be called butane, but it's in a ring, so we'll call it cyclobutane. And the pattern goes on: cyclopentane, cyclohexane, cycloheptane, cyclooctane. But again, if we just look even at the 2 of them, then we've got C3H6 and C4H8. So you can see the pattern is kind of similar to what we had for the alkenes. And indeed, the general formula for these guys is the same. CnH2n, which is a bit of a pain because it means that if I tell you I've got a compound here called C4H8, we don't know whether it's cyclobutane or whether it's butene, and that's something that we're going to look at later on. So that's our families. We've got the alkanes, we've got the alkenes, and we've got the cycloalkanes. Now the only thing different between them is that or within the one family, is that the molecules get bigger. Okay, so if we go right back to our alkanes, you can see that as we go down, all that's happening is the length of the chain is getting bigger. Okay, so propane, the 3, 4, 5, the length of the chain is getting bigger. If we look back at our data booklet, which I showed you how to get the cheat, what effect does that actually have? Well, the data here shows the melting point and boiling point of the alkanes. And you can see that as the molecules get bigger, the boiling point increases from minus 164 for methane up to 126 for octane. So the key thing is this, and this is the same again if you look at the cycloalkanes, 12, 49, 81, so again it's increasing, and we've got some of the alkenes here as well. And we can see that as we go up through the alkenes, their boiling point increases as well. So basically the rule is that for all these families, so if we look at their properties of hydrocarbons, then that as the number of carbons increases, so the chain length increases, then what happens is that the boiling point increases. Now if the boiling point increases, then what we have to think about is what other impacts will that have. Well, if the boiling point is higher, that means you have to have higher temperatures to turn it from a liquid into a gas. Okay. Now, what that means then is that the flammability and there's a clip showing what flammability means, but that basically means how easy it is for something to catch fire. Not whether it'll burn or not, but whether it'll catch fire. So you can think about wood. Wood's not particularly flammable. Okay, it takes a wee bit to get wood to burn, but it will burn. Whereas things like petrol obviously are very flammable, they catch fire very quickly. So as the number of carbons increases, flammability is to do with gases, okay, because it's gases that burn. So the easier something turns into a gas, the quicker it will catch fire. So if the boiling point is higher, then there will be less gas at room temperature, so its flammability will decrease. So there will be less gas to catch fire. Okay, so the flammability decreases. Yeah, there's another word that you have to learn about, and that's called viscosity. And viscosity is a kind of posh word for runniness. Alright? So something like custard is very thick and gloopy. Okay? That means it's got a high viscosity, whereas something like water flows very easily. So viscosity is a measure of how thick and runny something is. Okay? Now, if the boiling point is higher, and if we look back, the melting point is also increasing, then what essentially we're saying is that it's more likely to be a solid. Okay, so at room temperature it's getting more and more like a solid because it's getting further and further away from a gas because the boiling point's increased. So that means if it's more and more solid, it's getting thicker and thicker and thicker. That means then that the viscosity increases. Okay, so as we go from methane up to, let's say, octane, the boiling point increases, and again that's dead easy to remember because just look up the data booklet. But the impact on that is that the flammability decreases because there's less of it as a gas, and the viscosity increases as well because it's thicker, it's more like a solid. Okay, so you need to know these properties. And these properties are going to be very, very important because it'll help us separate the hydrocarbons out, because remember that's what we're trying to do here, and also it will link them to how we can actually use these hydrocarbons as well.